So last section in chapter 7 is on solving trig equations. A little bit with identities, but mostly with identities. A little bit with inequalities, but mostly identities. But we're solving them analytically. Analytically means using algebra. Okay, we're not really going to be taking a graph approach to any of these problems. So just to show you kinds of equations you're going to solve, we're going to solve equations that look like that. Maybe one that looks like that. Equations like that. Okay, so that's going to be the goal. Besides the algebra stuff that I just reviewed with you guys, factoring, quadratic formula, you need to know the ASTC chart. You're going to need some of the identities that we learned yesterday. Mostly, one of them has a double angle identity. If we get to it today, maybe, but maybe not. Maybe that'll be tomorrow. And the Pythagorean identity, sine squared plus cosine squared equals 1. That comes up a lot too. So, again, don't try to memorize all those identities. Put them on a reference sheet. Okay, that's the easiest way to do it. So, when we solve an identity, if we're lucky, it'll factor. That's the easiest way to solve it. But the important thing is, when you're trying to solve an identity, it's just like solving an equation. You can only have one variable in it to be able to solve it with factoring or quadratic formula. This is a quadratic equation. X squared plus 3x plus 4 equals 0. This is not a quadratic equation. The problem with that is now you have two different variables. You have an x and you have a y. Quadratic formula is not going to work on that. Okay? So, just like when you're solving an equation, you need to have only one variable in it, one letter. When you're solving trig equations, you can only have one trig function in it, like sines or cosines. You can't have a mixture of sines and cosines in the same problem when you're trying to factor or use quadratic formula. Now, if we get to the problem that's factor by grouping is a little bit different. That's another technique. Sometimes you do have more than one trig function. Every problem we start out with today, it's going to have one trig function. Okay. If factoring doesn't work, we can try the quadratic formula. Now, quick note about quadratic formula. If I just make up something like 8x squared plus 4x minus 5. When you use quadratic formula, what are you solving for in that problem? You're solving for what? You're solving for x. If you want to be technical about it, what you're solving for is the variable in the middle right there. That's what you're solving for. You're solving for x. So that's a very specific kind of quadratic equation. Basically, anything that fits this pattern is quadratic. What I wrote right here, that's a quadratic type pattern problem. The key for something to be able to be solved with the quadratic formula is, first of all, it has to have 3 terms. 1, 2, 3. The third term has to be a constant. Just a number. Plus or minus, doesn't matter. Whatever's in this box and whatever's in that box has to be the same. Like an x and an x, or a y and a y. Okay, it has to be the same letter or the same thing in each box. And the last thing is, the exponent on the first box has to be double the exponent on the second box. It could be a 2 and a 1. And that's the most traditional kind of quadratic problem you see. You have a 2 here, you have a 1 there, that's quadratic. If I write something like this, 5x to the 6 minus 4x cubed plus 7. That's a quadratic type problem. It has 3 terms. The last term is a constant, and that exponent is double that exponent. Now, if I asked you what you'd be solving for there, here, you're solving for x. If you use quadratic formula on that, a is 5, b is -4, c is -7. You go through and do it just like always, but you're not solving for x. You're solving for x cubed. So once you use quadratic formula, you're going to get an answer. You wouldn't write x equals the answer. You would write this. X cubed equals, and then put the answer in there from the quadratic formula. So this problem would have an extra step at the end. Okay? The extra step at the end would be to take the cube root of each side. And whatever you get after you do the cube root of your answer from the quadratic, that's the answer. So what we might see is a problem like this. 3 sine squared x minus 2 sine x minus 7 equals 0. That's a quadratic equation. It's got 3 terms in it. 1, 2, 3. Last term is a constant. It has the same trig function, sine, sine, so that's good. It's not like we're mixing sines and cosines. And this exponent is double that one if you really want to write it. A 2 and a 1. If you can solve this problem, then solving the one above it is exactly the same. There's no difference. All right. So what we're trying to get used to looking at in this section is equations that are quadratic type problems. Not necessarily the traditional one you're always used to seeing, but other ones that fit the pattern. Well, we're going to go through that especially when we get to one that's a quadratic formula. Okay. So, first thing to mention is that trig equations go on forever. Meaning, if you can find a solution in the first cycle, then that solution is going to occur again in the next cycle. And then again in the next cycle. And the next cycle. So technically, if you find one solution, there's infinitely many. We're not worried about finding infinitely many in this section. All we're worried about in this section is finding the answers where they tell us to find them. In this case, between 0 and 2 pi. Now, most of the time, if they ask me to find answers in radians, I'm going to do degrees first. If they want radians, I'll convert it by hand at the end. The reason why is because if you use radians right off the bat, like let's say I do second inverse sine of 0.5. You get that number. That's a radian. There's actually a much better way to write that, but your calculator is not going to tell you what it is. Watch if you do it in degrees first. Watch what happens. Second inverse sine of 0.5. I get a nice answer, 30. It's 30 degrees because I'm in degree mode. Now, if I take 30 degrees and multiply by pi and divide by 180, how many times does 30 go into 180? 6. So what I end up with is when I convert 30 degrees into radians by hand, I get pi over 6. Now, type that in, watch what you get. Pi over 6 is the decimal 0.52359. That was the answer that I got originally. But the problem is you're not going to recognize 0.5235987 as pi over 6. There's too many decimals to recognize. There's hundreds of them. But if you do it in degrees first, then you don't have to recognize it. You can do a problem in degrees, and then change to radians by hand at the end. Okay. So that's a trick that I'm going to use a lot of the time. So I don't have to write 0.523598. I don't want to see that. I want to see pi over 6. And that's how we'll do it. Now, sometimes, even if you do it in degrees first, you get a lousy answer anyway. So for some problems, no matter what we try to do, we're not going to be able to write it x. Okay? But generally, if the answer is a multiple of 30 or 45, there's a way to write it nicely. If it's not, then there isn't. But we'll just use a decimal. All right, so let's look at this one. 2 cosine squared x plus sine x plus 1 equals 0. Does that equation fit the pattern I showed you earlier for a quadratic? No. Not quite. It's close, but what's wrong with it?
Does it have an x?
It what?
Does it have an x or a variable?
So we have variables right there, right? X and x. So we got those. Yeah.
The second position isn't the same as the first.
Right, it fits everything except that. It's 3 terms, the third term is a constant, the first exponent is double the second one. The problem is here and here. One's sine, one's cosine. You can't have that. So, when you have a situation like this where there's 3 terms and it fits all the criteria I just said, you want to make a substitution. And what you want to do is you substitute for the squared term. Now, if you're wondering, what do you substitute? You use a Pythagorean identity. Okay? And I put one on the board that will help you with this one. So you're going to use a Pythagorean identity to substitute for the squared term. So this is going to change. We're going to have the 2. We're going to put something different in a minute. Plus sine x plus 1 equals 0. Now, using the Pythagorean identity, this is from section 7.4, but I put it in the video yesterday for you too. What is cosine squared equal to if you got it by itself in that identity? Well, what's preventing cosine squared from being by itself right now? What's there that we don't want? The sine what? Sine squared. So put the sine squared on the other side. How would you move sine squared? Subtract it. So you would have the 1 over there, just the way it was before, and subtract the sine squared. So now we've rewritten the formula, and cosine squared is 1 minus sine squared. So make this substitution right there. Change cosine squared to 1 minus sine squared. Now we have to do a distributive property, but once we do that, we'll be able to get this the way we want. All right. So let's do that. What's 2 times 1? 2. Plus we have 1 more at the end we can combine it with. 3. So I'm going to do that in one step. 2 times negative sine squared x. All you can do is this. Negative 2 sine squared x. Now, does this 2 get distributed to the sine x? No. Right. So now we have something that is a quadratic type pattern. Negative 2 sine squared x plus sine x plus 3. Now we're ready to solve this using all the same techniques you'd use in Algebra 1 to solve a quadratic. Any questions how we got into this stuff? Yep.
How did you get the plus 3?
So we did 2 times 1 plus 1. So we just distributed and combined like terms in the same step. Okay, now when we're factoring or using quadratic formula, you generally don't like to do it if your problem looks like this. I'm just making something up. You want it equal to 0, that's good. But what else do you want, especially having to do with the number in front of x squared? You want the number in front of x squared to be positive. Anytime you factor into quadratic formula, you always want this to be a positive. Same thing here. So what can you do when it's not a positive? How can you fix it?
Multiply everything by -1.
Yeah, basically just change the sign of everything. So you could have 2 sine squared x minus sine x minus 3 equals 0. Now we're ready to try to solve it. Now, what some people do because they get confused looking at all the signs in there is they rewrite it temporarily without the signs. So this step is optional. But if it helps, you can write this problem down. If you can factor this one, then you can factor the one above it. It's exactly the same thing. It's just the one below here takes the word sine out of it, so visually your brain's not as confused looking at more stuff. Right? But remember, if you factor it this way, you need to change your x's back to sines when you're done. Right? But if you temporarily want to write it like that, you can. So we would have 2 sets of parentheses. What would be my my first term in this parenthesis and my first term in that parenthesis? Well, it has to have x's in it, right?
Oh.
Because we're trying to multiply something times something to get 2x squared. Yep.
Minus 1.
You know what? Just start with that. 2x and x, which is really 2 sine and sine. Okay, we need to change it back to that in a second. So we got 2x and x. Now we have a negative middle and a negative constant. What does that mean about my plus minuses down here?
One of them is actually negative and the other positive.
Yep, you're going to have one negative and one positive. Which one you put where makes a difference. We might have to switch that. And now 2 numbers that multiply to give me 3. Three and 1. You can try it in that order. So now we just have to check that we have the middle. 2x times -1 is -2x. 3 times x is 3x. What's a -2x and a positive 3x? X. That's not what we want. We want -x. So what do we have to do?
Change the sign.
Just change the signs. Plus, minus. Okay. Now you're good. You factored it, but you should really write it back the way it was with signs. Okay? So these 2 steps are kind of a temporary step, if it helps you visually, to factor it. Now write it the way it should be. 2 sine x minus 3 sine x plus 1. Okay, so these are a temporary step. Which most of the time, honestly, I don't do that. It's up to you. All right, so you can check it, but we just did. 2 sine times sine is 2 sine squared. 2 sine times 1 is 2 sine. -3 sine. So 2 sine, take away 3 sine, is -1 sine. Perfect. -3 times 1 is -3. Okay. So now we have something times something equals 0. If 2 things multiply to give you 0, what does that mean?
One of them is 0.
One of them is 0. Either this one equals 0, or this one equals 0. So to get x by itself here, you start furthest, pretend like it's basically this. Pretend that that sine x is a block. You want to get what's in the block by itself. So you deal with everything outside the block first, and then we'll deal with what's inside the block last. So what's the first thing you would do here to start to get this block by itself? Yep.
Add 3 equals.
Yep. Add the 3, and then what?
Divide by 2.
Divide by 2. So I'm going to do that in one step. Add the 3, divide by 2. Now we got to get x by itself, so we have to get rid of sine. How do you get rid of sine? You have to use inverse, yep. So we have to take the inverse sine of what's on the left, take the inverse sine of what's on the right. That cancels. And now, think about 3 over 2 for a second. What is 3 over 2 as a decimal? Yeah.
1.5.
1.5. If you graph sine, what's the highest that it normally goes? 1. So does it ever hit 1.5? Then this part isn't going to be doable. Right? It's not going to work. If you try to type it in, the inverse sine of 1.5, doesn't matter if you're in degrees or radians, you're going to get an error. Because the domain for inverse sine is -1 to 1. 1.5 is outside the domain. So, it doesn't mean that the problem has no solution, because we still have this one. It just means the left side didn't give us any answers. Now we look at the right. Brianna, how would I get sine x by itself here? Subtract 1, and now we're going to do the same thing again. Inverse sine on each side. Now, before I look at that, let's think about it. Does the graph of sine hit -1? Yes, it does. For this one, when it's a number like -1, +1, or 0, we're going to look at the graph. That's the best way to do it. There's your beginning, quarter, half, 3/4, all the way through the cycle. Where does the sine hit -1? Well, 180 is where it hits 0.
270.
That's 270. It's okay to write that in degrees, like he just said for now, but remember, they want radians. So we can write 270 temporarily. Does it hit anywhere else? Does it hit -1 anywhere else in that cycle? Think here? No. It hits 0 a couple times in the cycle, but it doesn't hit -1 more than once. So x is 270. Or when we convert it to radians, multiply by pi, divide by 180, you get 3 pi over 2. So because of the restriction they gave me on the domain to start with, 0 to 2 pi, I know they want radians. If they had said 0 to 360, then I would know they want degrees. So I have to pay attention to that. Okay, and that's the basic idea of every problem. Sometimes this other side works and you get more answers. This time it didn't, but we're going to do somewhere where it does. Okay. Any questions on that first one so far? Okay. All right, let's look at this one. Now, it does say find all solutions in one period. On the test, I will tell you where one period is. 0 to 2 pi. So you're not going to have to worry about figuring that part out. I'm going to tell you that it's 0 to 2 pi. Because if you don't know this, then you don't even know where you're looking for answers. That's it. Okay. What's different about this equation compared to the first one we did? Yeah. Okay, the first one had sine and cosine, no? Right? So the first one had sines and cosines in it. This one has sines and cosines in it. But there's something else different. Yeah?
It's not equal to 0.
Right, it's not equal to 0. So the first thing you want to do is get it equal to 0. And what did I say about the squared term? You always want that to be what? Positive. So you might wonder why I'm about to do what I'm going to do, but I'm going to move everything to the right. You might be thinking, well, if you do that, you're going to minus the 2 sine squared x, and it's going to be negative. It's only going to be negative temporarily, because watch what happens. Okay? So we're going to minus 2 sine squared x from each side. So now the 2 sine squared x is on the right. Cosine, still on the right. And the plus 1 is still on the right. Okay. Any question on the first step? Right. So now it's equal to 0. And is that a quadratic equation?
No.
No. Not a quadratic. So how come? Why isn't it a quadratic?
Terms are
The terms aren't equal. What do you mean?
like the sine and cosine are supposed to be the same.
Right, yes, you're gonna have the same trig function in each term. Exactly. So when they're not equal, I gave you a hint at which one you always substitute for. Which one is the one that we're gonna change? Chris? Nope, not the cosine. Substitute for the squared term. Okay, so always substitute for the squared term, which is sine. So what I'm going to do is just go like this. Into space, because you're going to fill something in for sine squared. I'll copy everything else. Now, what you're going to plug in for sine squared, you have to remember your identity. Sine squared plus cosine squared equals 1. Based on that identity, what is sine squared equal to?
One minus cosine squared.
1 minus cosine squared. So he just took cosine squared, minused it to the other side. Now, what do I have to do next with that -2? Emily? Distribute. Now maybe you can see why I moved the squared term to the right. So you can see what's about to happen to that squared term. So just go through distributing it. Eric, what's -2 times 1? Plus 1.
-1.
So I distributed and I combined my constants all in the same stuff. Brandon, what's -2 times negative cosine squared?
2 cosine.
Yep. And the squared term automatically just became positive. Had you not done what I did, you put everything on the other side, what you would have now is a negative squared term, and you'd have to fix it just like we did the first time. The way Jared said, divide everything by -1, or multiply. Okay? But because I was clever about how I did it, I can avoid that step. And Nakira, what else do I still have to copy down? Yep, cosine x. Okay. So now we're going to try to factor it, just like we did last one. 0 equals. Let's try to factor it this time without doing that temporary step of changing all the cosines to just x's. See if we can do it. What would your first term be in each parenthesis? A what and a what? Emily? One of them would be a cosine. What about the other one? It wouldn't just be a cosine, because then cosine times cosine would just be cosine squared. But I want 2 cosine squared. So what would I have to put here? Yeah, 2 cosine. Okay. Positive middle, negative constant. What does that mean about my pluses and minuses? They can't be the same, no.
One is positive, one is negative.
Anytime this is a negative, you have to do something times something to get a negative, which means you need one of each. Whether it's plus minus or minus plus, we haven't gotten that far. And then 2 numbers that multiply to give me 1. 1 and 1. Let's check it. 2 cosine times -1 is that. 1 times cosine is that if you combine a -2 and a +1, do you get what I have right there? No, it's wrong. So what do we have to fix? Just switch the signs. Make that a positive, that a negative, and now 2 cosine times 1 is 2 cosine. -1 times cosine is a negative cosine. 2 cosines take away 1 cosine is 1 cosine. Perfect, it factored. Now, a lot of people get confused in the homework because in the homework, the problem starts you off at this step. And they say, I don't know what to do. Well, it's already factored for you. So a lot of the problems in the homework start you at this step. You don't even need to do any of these steps up above it. Okay? On the test, when you go through a problem, you're going to have to do the full problem. But in the homework, they may start you at this step right here. So now, if you were at this step, what do you do from there? Emma? Yep, the 2 factors. And what do you set each factor equal to? Yep, set that equal to 0. Set that equal to 0. Let's do the one on the right first. That one's going to be easier. The one on the left is going to involve the ASTC chart that I reminded you about. It's going to be the first time we've had to use it. So, for this one, cosine x equals what? -1. I think we just, maybe we did sine x equals -1. I don't remember. So x is the inverse cosine of -1. Anytime that this number is a -1, 1, or a 0, draw the picture. Cosine looks like this. Start, quarter, half, 3/4, end. Where is cosine equal to -1 here? Yeah, at pi, yes. If you were thinking 180, you're not wrong. You just wrote it in degrees and they want radians. So pi. Now, let's look at this one. What would be my first 2 steps to get cosine by itself?
Add 1 to each side and then divide by 2.
Add 1, divide by 2. Perfect. Now you have that. How are you going to get rid of cosine?
Inverse.
Yes. Now, the problem here is it's equal to a half. You can't visualize that on the graph easily. You can visualize the highest, the lowest, or the middle. That's 1, -1, or 0. A half is too hard to figure out. But we could at least look at the graph and figure out how many times it's going to hit a half. Draw in a line at a half. How many times does it hit it? Twice. So we are looking for 2 answers. The calculator will give us the first one. So x equals the inverse cosine of a half. All we have to do is type that in. Now, they want radians, but my suggestion was to always do it in what first? Degrees. I mean, if you do it in radians, watch what happens. If you do it in radians, inverse cosine of a half is the decimal 1.047. Does anybody recognize what that is as a fraction of pi? I mean, I do because I've done a lot of them, but so the point is you're not going to recognize that that number is really this number. It's pi divided by 3. But you're not going to recognize it by looking at that decimal. That decimal's not going to help you at all. What is going to help you is doing it in degrees first. So do it in degrees. Second, quit. Now type in the same problem that we just did. Inverse cosine of a half. And look what happens. This time you get a nice answer. 60 degrees. The only problem with that answer is they don't want degrees. But that's okay. It's still right. Just change it by hand. 60 degrees. What do you multiply by to change it to radians? You're going to divide by 180.
Or pi.
But you're going to multiply by pi. 60 goes in once, and how many times does 60 go into 180? Yeah, 3, and that's exactly where I got pi over 3. Okay. So the answer we get here is pi over 3. All right. Any question on that one? Now, we said that it hits 1/2 twice. Yes.
Mr. Shannon wants the box of calculators now.
They're in the math department closet. Tell him he'll know that. He'll remember. I told him. So it hits twice. Well, you've only found one answer. You've got the 60. Let's think about how we get the second answer. And it's going to be easier to do the second answer with the 60 and then change to radians after. It's very difficult to do it with the pi over 3. Arithmetic gets kind of messy. Draw your chart. Go back and look at this. Cosine x equals 1/2. What kind of number is 1/2? Positive or negative? It's positive. So you are looking for where the cosine equaled a positive number. Well, that happens in 2 spots. Here, cosine is a positive number. In fact, they're all positive here. What's the other quadrant where cosine is a positive? Chris? Quadrant 1, 2, 3, or 4.
The second quadrant?
No, in the second quadrant, only the sign is positive. We're looking for where cosine is positive. Yeah. The fourth one. So we're looking for an answer here and here. We already have one of the answers. What did we get for the first answer? In degrees. So that, I mean, for this part over here. 60. That's there. So you have 60. What you need is to get an answer in quadrant 4. There's a formula that you use to get an answer in quadrant 4. And I showed you guys what it was for each one. What do you do with your reference angle to get an answer in quadrant 4? Yes. Remember, this is 180 minus reference angle, 180 plus reference angle, 360 minus reference. So the other answer is 360 minus 60, which is 300. Now, 300 is correct, it's just not the units, they want radians. So a quick way to do this is, what do you multiply 60 by to make it 300? Yeah, 5. So this answer is 5 times as big as the first one. So just take this answer and multiply it by 5. 5 pi over 3. And I'll put this one here. So these 60 and pi over 3 are the same answer, degrees and radians. 300 and 5 pi over 3, same answer, degrees and radians. Now, very easy to check. If you take the cosine of 300, it better equal 1/2. If it doesn't, then we didn't solve the problem correctly. Cosine of 300 equals 0.5. You could check the 60. Cosine of 60 is also 0.5. It's exactly what you wanted. And you could check this one if you wanted. That's 180. Take the cosine of 180 and it should come out to -1. If it doesn't, then we did something wrong. But it does.
Why do we have to find one in the fourth quadrant?
Well, first, do you know why we had to at least find a second answer?
Yeah, because
Okay.
it intersects twice.
Because it hit twice. The reason we picked the fourth quadrant is because this says cosine equals a positive number.
Oh,
Right? If cosine is equal to a positive, there's two spots where that happens,
What if
here and here.
it said cosine equals negative?
If the problem was cosine equals a negative number, then you'd be looking for where cosine is negative, which is here and here. So
would you get two more answers for that?
you would have just two answers.
Oh.
Just two answers. You only get two answers at a time. Yeah, two answers at a time. You're never going to have to deal with all four quadrants at the same time for the same thing. You only have to deal with two at a time. Okay. All right. Any question on that one? And again, don't get confused in the homework because they will start you off at that step in a lot of problems, which is like 3/4 of the way through the problem. They may even start you off at this step in some of the problems, where they even did the factoring for you, and all you have to do is add 1, divide by 2, and do the inverse cosine. Okay. All right, let's try one more, and probably stop with that one. I think actually this is example 3, isn't it? That was example 1. Oh, I just called that number 15. So whatever. Okay. So tangent x equals 3 cosine x. For this one, I'm going to have to give you a little bit of a hint. It's a little different, but once you do this hint, then it's the same. What trig function have we been, or trig functions have we been dealing with in every problem so far? Sine and cosine. So let's change everything here to sines and cosines. That's a trick we've used before, so let's try it here. Do I have to change anything on the right to make it what Jared just said? No. How about on the left? How can you write tangent in terms of sines and cosines? And I mentioned this yesterday when we did the sum and difference identities. I said if you really didn't want to memorize the tangent one, you could just do it this way. You don't really need the tangent one.
Sine over cosine?
Sine over cosine, exactly. Sine over cosine. Now, the only thing I don't like about that is now we have a fraction. So, what could I do so that I don't have a fraction?
Multiply by cosine?
Yep, exactly. Multiply everything by cosine. And from here, it's going to look just like one of the problems we've done before. Cosines cancel. We have sine x equals, what's 3 times cosine times cosine? Yep, 3 cosine squared. Now you've got a trig function on one side, that's sine or cosine, and a trig function on the other side, that's sine or cosine, and one of them is squared. It's exactly what you had right here. Trig function on one side, that's sine or cosine, trig function on the other side that was sine or cosine, and one of them was squared. So it's the same. So let's go through it. Well, two things. When we're solving a quadratic, we always want to get it equal to what number? 0. So what I'm going to do is put that on that side. Again, you might be thinking, why? Because don't you want the squared term positive? It will be. So put the squared term on the left. So you would have this. Okay. Now we've got everything on one side. That's good. Is that a quadratic equation?
No.
No. Why? What's wrong with it?
The terms are not equal.
Right. You've got to have the same trig function. You can't mix sines and cosines. So you have a choice. You can substitute for the cosine or the sine. But I gave you a hint which one to always substitute for. And the one we should substitute for is
Cosine squared.
the cosine squared. Yeah. Now, we've already substituted for cosine squared earlier. Anyone remember from the notes what cosine squared equals? Yeah?
1 minus sine squared.
Yep. Okay. And now let's distribute that and make it look like a quadratic. So I'm going to do that part first. That's 3 sine squared x plus sine x. And I didn't forget about distributing that. I'm just going to do that at the end. Minus 3. Okay. Is that a quadratic?
Yes.
Yes. Perfect. It is a quadratic. Unfortunately, it doesn't factor. You can try really hard, but you're not going to be able to factor that with nice numbers. So if you can't factor a quadratic, what's the other way that you can solve it? Yeah.
Quadratic formula.
Quadratic formula. So this is the first one we've had to do with quadratic formula, so let's see what happens. What would A be? Okay. B is 1, and C? -3. Now, very important to remember, you're going to do quadratic formula just like you always do it, but you're not solving for x. What are you solving for?
Middle.
Which is what?
Sine of x.
You're solving for sine of x. So when we're done quadratic formula, we're going to write this. Sine x equals, and we're going to have something in that box. What goes in that box is the result from the quadratic formula. That's what goes in that box. Okay, so let's go through quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Minus a minus is going to become plus. What's 4 times 3 times 3? 36 plus one more. 37. So you can see now why you couldn't factor it, because the square root is a messy number.
Wait, wouldn't C be negative?
It was, but we had minus a minus.
Oh.
So remember, it's b squared minus 4ac. So you had minus, and c was negative, so it makes it a positive. Right. So now, what does this equal? Is this x? Is that the answer? So what did we just solve for?
Sine.
We just solved for sine of x. That's not x. If this was a regular quadratic problem that just said x squared plus x minus 3, then you would have solved for x. That goes in this box. So now the question is, how do you get x by itself? Yep. Yep. Take the inverse sine of each side. So inverse sine of negative 1 plus or minus square root 37 over 6. Right? So really, there's a couple answers that you're going to get. This problem could have up to 4 answers. You could do the plus, and then the ASTC gives you 2. And you could do the minus, and then the ASTC chart gives you 2. So you could have up to 4. Let's look at it. What's the highest and the lowest that the sine function goes? From what to what? 1 to negative 1. So this number has to be between 1 and negative 1 for it to work. I'm going to do the minus first. I'm going to do I'm just going to do what I circled. Negative 1 minus, oops, sorry about that. It's 37. -1 minus the square root of 37. And now divide that by 6. Is that number between 1 and -1?
No.
No, so you can try to do the inverse sign of it if you want, but it's just going to give you an error. So here, the minus, we can cross it out. You don't need the minus. Let's try the plus. Second inverse sign, -1 plus the square root of 37, and then divide by 6. Oops. I don't want that. -1 plus the square root of 37, divide by 6. Is that number between -1 and 1?
Yeah.
Yes, then that number works. So I'm going to do the inverse sign of what's circled, which I already typed in on the calculator, the 0.4712. Now, it doesn't matter if you do degrees or radians here, because if you're using quadratic formula, you're already into messy answer land anyway. So you can do degrees first, you can do radians first. It's not going to come out nice either way. So I'm just going to do this problem in degrees. I could change it to radians by hand after if I really wanted, but let's just do it in degrees. 57.90. Approximately. And now we have to think about that ASTC chart. When I typed all this in, -1 plus the square root of 37 over 6, I got 0.84. Is that a positive or a negative number?
Positive.
Positive. So what two quadrants is sign positive? If you can figure that out, that tells you where your answers are.
First.
Yep, first and second. You already have one of those answers. We already found it. 57.9. Where is that answer? Quadrant. Quadrant 1. You already have, so that's in quadrant 1. What do we call that 57.9? That's my, begins with an R. It's my reference angle. That's the angle that I use as my reference to get the other answer. Okay. So we're in quadrant 2 for the second answer. We just figured that out. What's the formula in quadrant 2 with your reference angle?
Yep. 180 minus the reference angle.
180 minus the reference angle. Don't leave it like that. 180 minus 57.90. 180 minus 57.90 gives me 122.10 if I'm keeping my accuracy. So I got that, and I got that. Now, if they really wanted radians, I would multiply by pi and divide by 1. Each one of those answers, just by. And they're still going to come out messy. But it's a lot easier to do the ASTC work in degrees than it is in radians. Because if you're going to do it in radians, instead of being 180 minus, 180 plus, and 360 minus, now your formulas turn into pi minus, pi plus, and 2 pi minus. So now you have to do arithmetic with pi to get the second answer. It's a lot easier to do arithmetic without pi. So do it in degrees first, and then manually change to radians after. Okay. Any questions on that? All right, so most of the problems in the homework, in fact, I think every one of them is going to start you off at either this step right here or this step right here. You're not even going to have to do the factoring, the trig substitution, or getting it equal to 0. We'll practice more of those in the homework tomorrow. All right, so homework for tonight. All right, I'm going to change that a little bit. We're going to do 1 through 9 odd. Tomorrow I'll give you some of those evens. 11 is okay. 13, I'm going to add that to tomorrow's homework. 14, we're going to do that tomorrow night. 16, we'll do that one tomorrow night. 19 will be tomorrow night. So this is the homework for Tuesday night. That's the homework for Wednesday night. So 2 through 8 even, and then 13, 14, 16, 19. Okay. So we'll spend another day on this section. We might finish it early. If we do, we'll start 8.1. If we don't, we'll spend the whole day tomorrow on the same section.